Hey, you! Yeah, you, I'm talking to you. What's a guy gotta do in the heart of New York to get a bacon, egg, and cheese? I mean, I've been looking for hours and I still can't find a spot that'll give me one. I mean, a bacon, egg, and cheese in the middle of New York? It's absurd. Preposterous, even. You could even call it radical. Hi friends, did I just do all that so I could put on a New York accent and make a joke using the word radical? Maybe I did, and what are you gonna do about it? Jokes aside though, we are here in our 6th class of Unit 6 to continue using our Properties of Radicals, Part 1. If we're gonna do that, it might behoove us to remember what those properties actually are. Take a look back at your notes, 30 seconds. Give me those 4 properties of radicals that we created together. Go! And stop. First up, if I take the square root of a perfect square, which we expressed as so, we know that it could be either the positive or the negative version of that number being squared. If I multiply it by itself, either way, I'll get a positive answer. And if I take the cubed root of a perfect cube, which we write like so, here we don't need a plus or minus, but we did observe that the sign of our final answer will always be the same as the sign of the thing inside that radical, which we of course call our radicand. Now, this works for any even power, any even index requires a plus or minus symbol, where we don't for something like a 5th root or a 7th root or a 9th root. But we, in this class, are just going to concern ourselves with square roots and cube roots. Number 2 and number 3, our product and quotient properties. The product property, number 2, says, if I take some root of a product of things a times b, well, that would be the same thing as taking the product of the roots of each factor individually. Same thing for division. If I take the root of some quotient, a divided by b, well, that's the same thing as taking the root of the numerator and the root of the denominator separately. And last but not least, we saw if we take some number x of some root, we'll call it the nth root of a, and I add that to some number y of the same type of root, well, just like terms, I can think of these. We in fact called them like radicals, like units, right? Here, all I need to do is add up their quote-unquote coefficients, x and y, smush it right back up against that root, and that's how many of that type of root I have. Nice! When we were together last time, we got a little bit of practice using them. To really make sure they sink in, I've got 6 examples for you. I want you to simplify using what you know about your properties of radicals. Take 2 minutes, see how far you get, and see what you get. Go, go! Alrighty, come back. So, the square root of 12. Again here, I remember from last time that I do not want to leave any perfect squares here under a square root. So if I think about factors of 12, well, 12 is 4 times 3. 4 is a perfect square. So I can, using the product property, split this into the square root of 4 times the square root of 3. Now, the square root of 4, I know, is plus or minus 2. I can't simplify the square root of 3, so it just gets smushed right back up. Plus or minus 2 root 3 is my final answer. Same thing for number 2 here. I can't leave any perfect cubes inside of 80. So I know that 80, this is where my list of perfect squares and cubes is going to be really helpful for me. 80, you'll notice, is 8 times 10. 8 is on our list of perfect cubes. So using my product property, I'm going to split this down as the cubed root of 8 times the cubed root of 10. From here, I can simplify the cubed root of 8. That's 2 times 2 times 2. I cannot simplify the cubed root of 10 any further. Smush it right back up against that 2. 2 cubed root of 10 is my final answer. For number 3, the cubed root of 27 over 125, well, by the quotient property, I can take my cube root and give it to the numerator and the denominator separately. Now I can simplify the cube root of 27. Well, 27 is 3 times 3 times 3. The cube root of 125, the number that multiplies by itself 3 times to get 125, is positive 5. So 3/5 is my final answer. Again, it's a cube root, no plus or minus needed. For the square root of 45 over 4, though I might need to do a little bit more work, using my quotient property, I can rewrite this as the square root of 45 over the square root of 4. Now, the square root of 4, I know what to do. That's 2. And then the square root of 45, again, I need to look for factors of 45 that are perfect squares. Notice that 45, that's 9 times 5. So splitting this up using my product property, the square root of 45 is the same as the square root of 9 times the square root of 5. Simplifying that square root of 9, this is 3 root 5 over 2. We took a square root, so we add back in a plus or minus. So plus or minus 3 root 5 over 2 is my final answer. Square root of 47 times the square root of 47. We saw last time that if I multiply any square root by itself, by definition, this is the thing that multiplies by itself to get 47. So if I multiply it by itself, I should, of course, get 47. But I technically took a square root. I need to add a plus or minus. So plus or minus 47 is my final answer. And finally, for number 6, here, this is my last property. Again, I'm just counting like radicals. Notice that I have 2 root 6s. I subtract 5 root 6s. How many root 6s do I have? Well, that would leave me with -3 of them. And then I've got 4 root 5s. I add a root 5 to that. How many root 5s do I have? Well, I should have 5 of them in total. So -3 root 6 plus 5 root 5 is my final answer. Lovely. Now for the next 2 classes, just like our laws of exponents, we've seen how each of these work on their own. The name of the game for us now is iteration. In other words, we want to apply them in some cases with some more moving parts. But don't be frightened. When in doubt, remember to chunk it out and use that mathematical superpower of making it look the way you want it to look. As a bit of trivia for you that is going to be kind of important for us, there is one look that mathematicians like to avoid, and it happens in a case like this. Say I want to simplify the square root of 4 over 3. Now, first move should be relatively easy to make. Hopefully you agree by the quotient property, I can break this down as the square root of 4 over the square root of 3. Now, the square root of 4 I can simplify. That's plus or minus 2, but I'm going to hold off on the plus or minus for now. I'll leave this as 2 over root 3. Mathematicians, for whatever reason, by convention, do not like to leave square roots or cubed roots in the denominator of a fraction. I say for whatever reason, but there is a reason. It's a holdover from back when before we had calculators. It's much easier to approximate the value of a fraction when its denominator is a nice whole number. When I throw in a radical symbol, it gets a little bit harder to do. So the convention is that we do not want to leave any radicals in the denominator of a fraction. So I need to think creatively about a way to get rid of a radical in the denominator of a fraction. Take a risk, take a chance. Be wrong, who cares? What do you think I could do to this fraction to make it so that the square root of 3 is no longer in the denominator, so that that radical sign goes away? Alrighty, maybe you got it, maybe you don't. Roll with me, it's a kind of weird choice. I want to get rid of a square root in the denominator. Well, the easiest thing for me to do, if I want to get rid of the square root of 3, well, remember, as we saw above, if I take the square root of 3 and I multiply it by the square root of 3, that would be one way to get rid of my square root symbol, because root 3 times root 3 is just 3. But this is a fraction, which means I can't just multiply the denominator by the square root of 3. If I do something to the bottom of a fraction, I also need to do it to the top. Otherwise, I change the value of my fraction. So here, I'm going to make this choice. I am going to multiply by the square root of 3 over the square root of 3, which is, by the way, 1. Right? If I divide anything by itself, I get 1. The name for this strategy is called rationalizing the denominator. Now, in the word rationalize, you should hopefully see the word ratio, which of course means fraction. We also see the word rational. I know that the square root of 3 is an irrational number. So my goal is to make it rational, in this case by multiplying it by itself. The idea behind rationalizing the denominator, I am going to choose to multiply my fraction by a form of 1 that eliminates the radical in the denominator of the fraction. This particular form of 1 that I'm going to choose is root 3 over root 3. From here, all I need to do is multiply these fractions. Well, if I multiply across, 2 times root 3, my numerators times numerators, gives me 2 root 3. My denominators, root 3 times root 3, we've established is 3. And just for good measure, we did it with a square root. Let's add in a plus or minus. Look at that. I've got an equivalent fraction that no longer contains a square root in the denominator. There we go. Now, let's get a little bit of practice rationalizing. I'm going to take each of these fractions. I want you to tell me how each one would fully simplify. You might need to do a little bit of rationalizing here. Go ahead, take 2 minutes, see how far you get. Try it out on your own. And stop. The square root of 16 over 7. So using the quotient property, once again, my first move is going to be to split this up into root 16 over root 7. Again, 16, I know what to do with. That is 4. And then the square root of 7, I can't do anything with. But I can't leave a square root in the denominator. Let me multiply by the square root of 7 over the square root of 7 to get rid of the square root sign in my denominator. Well, here in the denominator, the square root of 7 times the square root of 7 is going to give me, unsurprisingly, 7. And then multiply across, 4 times root 7 is just 4 root 7. I got rid of a square root symbol in the denominator. Let me add back in my plus or minus. So plus or minus 4 root 7 over 7 is my final answer. Number 2, the square root of 9 over 2. Once again, I'm going to use my quotient property, break this down into root 9 over root 2. From here, again, I cannot leave a square root in the denominator. Simplifying my numerator first to 3, I'm next going to multiply by the square root of 2 over the square root of 2. I'm choosing a form of 1 that allows me to eliminate that root 2 in the denominator. Well, root 2 times root 2 in the denominator is just 2. 3 times root 2 in the numerator gives me 3 root 2. I got rid of a square root sign. Let me add back in a plus or minus. Plus or minus 3 root 2 over 2 is my final answer. And last but not least for number 3, the square root of 98 over 10. I could get started from here, but you might notice that 98 and 10, both of those are divisible by 2. So simplifying my fraction here, let me divide 98 by 2 to get 49, and 10 by 2 to get 5. From here, I'll split this up using my quotient property. This is the square root of 49 over the square root of 5. The square root of 49 is plus or minus 7, but again, I'm going to hold off on the plus or minus for now. I have 7 over root 5. Again, I need to get rid of the square root of 5 in the denominator. Let me do so by multiplying by root 5 over root 5, a form of 1 that does not change the value of my fraction, but does get rid of that square root symbol in the denominator. The square root of 5 times the square root of 5 is 5, and in the top, 7 times the square root of 5 gives me 7 root 5. Again now, plus or minus 7 root 5 over 5 is my final answer. Lovely! Now that we have this skill, we can in fact define what we will call our simplest radical form. There are 3 criteria to our simplest radical form. Question for you, what do you think that some of those criteria might be? Take a risk, take a chance. What are some of the things that we think we might want to avoid in the final answer of a fully simplified radical expression? Once you think you've got them, come back to me and we'll check. Alrighty, first up, the first big thing that I want to make sure of. We've already established step 1. I need to make sure that I do not leave any perfect squares under a square root or any perfect cubes under a cube root. So step 1, we want to make sure that we are not leaving any perfect nth powers under an nth root. Nice! For our second thing, this is one that we haven't quite encountered yet. However, we do generally want to, just like exponents have a single copy of each variable in the fully simplified form, for radicals, we want to make sure that there's only one radical symbol in our final answer. So we should say here, for number 3, actually, sorry, I've skipped a step, but I've gotten too far into the video to bother re-recording this. This is step 3. We are going to say for step 3 that there is going to be no more than one square or cube root in our final answer. So no more than one of our radical symbols. And then I'll include here in parentheses per term. For each of those things that are connected by multiplication, that's fine. But for example, when we were up above doing 2 root 6 plus 4 root 5 minus 5 root 6 plus root 5, we got to 2 different types of radicals. There was a root 6 thing and a root 5 thing joined by addition. That is totally okay. But within the addition and subtraction, each of those terms, we need to make sure there's only one type of root symbol. And last but not least here for our second step, working backwards, just like we did above with rationalizing, we need to make sure that all of our denominators are fully rationalized, which means we generally want to make sure that we do not leave any square roots or cubed roots in the denominator of a fraction. Yay! With that, we've got our goal for any radical expression. In class tomorrow, we will continue to play around with these properties of radicals and see how we can figure out how to arrive at that simplest radical form.